With that, let's go ahead and get started with the Facebook Data Center. Happy to introduce Najam Ahmad, who leads the networking team here at Facebook.
Thank you. Thanks. Hi, everybody. It's awesome to see so many people here. Most of you I know we've met in different forums. I'm going to try and be quick about my conversation. It's just going to give you an overview of our data center strategy and the things we're trying to work on or solve. And then the real fun part will be after me with you all and Alexei. They'll go deeper into the specific solutions that we've built. So switching from the conversation that Michael was having about latency and how they're building microwave, now we're jumping inside the data center. It's all about gobs and gobs of data, terabits and terabits and terabits of traffic, primarily driven out of machine-to-machine traffic. You guys have seen this graph before, I think. The yellow part represents machine-to-machine traffic, and the green part represents machines-to-user traffic. And that machine-to-user traffic is actually not insignificant. That's a horrendous amount of traffic, but in comparison to machine-to-machine traffic, it's dwarfed. And you can see also the growth rate of what's growing faster. The machine-to-machine is really just driving all the work that's happening inside the data center. So the real conversation here is not as much about latency, but about the volume of traffic and how do we provide enough bandwidth to machines to talk to other machines. This isn't a structure we've been using for a while. This sort of architecture got us to about 1 billion users. But how far can it go is the conversation. We used to call it our 4-post architecture. It's essentially designed around 4 large switches in the middle that act as our aggregation points. And the circles at the bottom, RSWs, are the TopIraqs and represents 1 rack. So each RSW represents 1 rack. All layer 3 structure. But the size of this structure was primarily limited by the size of that CSW box that we can buy. So we were buying the largest box possible that the industry had. And so the cluster size was essentially limited by the size of the box that we can buy. It also puts us in a situation of sort of a vertically scaling environment that we just need the next bigger box and the next bigger box. So what we've been working on over the last 18 months to 2 years is essentially switch to a completely different topology, a different architecture, which is more horizontally scaling. And then think about components that are far more simple, and we can continue to horizontally grow the environment. So in terms of data center, if you look at these 4 clusters, the traffic actually is what the interesting part is. So if you look at our traffic, the yellow bars, that's the intra-cluster traffic. So there's a lot of traffic that is essentially going from rack to rack, which is in some, if you read some papers, you would see it be a little bit counterintuitive. A lot of people think that traffic is actually inside the rack. In our environment, traffic is not actually inside the rack. So we've just represented a few different services. And even if you look at the overall, the majority of the traffic actually wants to go rack to rack. So what that means is that cluster size becomes an interesting conversation for us. Because of this architecture, we're limited in the size of cluster we could build, then it becomes a packing problem. So we're building, say, front-end clusters. We need some front-end machines, some memcache machines. What's the ratio of front-end to memcache? How we pack them. If one grows faster than the other, then it becomes an interesting packing problem, and then you start moving physically things around to make them fit inside a cluster. That itself is a fairly hard problem to solve. Anything that you have to do at a physical level is always too slow and costs too much. So anything you can change and modify logically through software tends to be faster and quicker. Right? So if you look at the traffic volumes, we needed to solve this problem where our clusters needed to be bigger and be able to have a lot of traffic between racks. So what we set out to do is essentially build the entire data center as one cluster. But we wanted to build an architecture that actually you can start with a small size and actually grow to the entire data center floor if you wanted to. But before I go into the solution on how we solved it, our problem is also about control, config, monitoring. Anybody who runs a network will tell you this. So traditional networks are built primarily around configuring each device based on role. And he's talked about it in the morning about configuration. It's essentially want to get down to a top-down configuration model where you configure the entire topology and a system then configures individual elements. Or in other words, in a lot of ways, manage every network device much like we manage servers in the environment. If anybody manages servers, you guys probably know when the server misbehaves, you don't really try to troubleshoot it too much. You just whack it and rebuild it, right? In the network world, we don't do that. We try to troubleshoot it and change configurations by hand, and that's a really bad thing to do. So moving towards an environment where each element is managed more like a server, and configuration is essentially done at a topology level. Each element has its own config. And I think Anis covered a bunch of this conversation in the morning as well. So what we ended up doing was build this. Interesting enough, a lot of people said, hey, this is what's sort of the innovative part about building a Clo network. Clo's been around since the 1950s. Yes, as a topology, it's been around since the 50s or a long time. What we've done in this environment, and Alexi after me is going to go and sort of go talk in detail about what that topology looks like. But the whole idea was that can we build a topology that you can deploy for a small set of racks to a whole data center floor. And every rack has an equidistance path to every other rack in the environment. And then we can build capacity as needed as well. So you could deploy this topology in a 4-to-1 oversubscription. Or if you wanted, you can go to 2-to-1 or even 1-to-1. So the topology, as we've built it, is scalable enough. You can go from a small to large and from 4-to-1 oversubscription all the way to 1:1 oversubscription as you need it. And that was the real key about building a topology that made sense. The TopIraq was the first switch that we built. We announced this, about 6 months ago. It's called the Wedge. And one of the things that's different about this switch was primarily that it has a microserver on board. So we put a microserver on this device itself. It also has a BMC chip. As you guys may already know, most of the server environment is actually managed by BMCs. And this is what's happening on the switch side as well. So what that allows us to do is use a lot of our tooling and development environment we already have for our server fleet. We have a pretty large server fleet that we manage, but for network, we have a separate management system. That is changing. And that's why we ended up building a TopIraq platform that actually can leverage the environment that we use in the server side. So if you combine the TopIraq with the work we've done on what we call Fbus, it's a Linux-based operating system that we built to run on these boxes. We solve our problem of building an environment that is actually managed much like the server base. And Alexi is going to go into great detail about the fabrics. I'm not going to cover too much on this. The next piece that I'm going to talk about is something that we haven't talked about in publicly yet. But if you look at this topology, we've built the TopIraq, but the next piece is actually the switch. This is the spine switch that we've been working on. It's an interesting design in some ways where the name is interesting, actually. We're all working on the six-pack part. So if you look at this chassis, it's actually a pretty simple design in some ways. We took 12 of the wedge boards, wedge the same thing that was in the TopIraq, and we stick them into a chassis. 8 of them have front-facing ports, and 2 of them act as the backplane. So you're essentially, what you end up with is a multiple instances of wedge inside the chassis itself. And our intent is to use this as the spine switch in our topology. And Alexi's here, Yuval's here to talk more detail about it. So again, 12 independent wedges, 4 fabric, 8 front panel. As everything that we're doing, we want to build an open platform. The idea is that, one, we're going to make this spec open source, probably via OCP. And we're using all Ethernet, so it's pretty standards-based. If you want to do Ethernet, this is all Ethernet, nothing else. But the idea would be to allow other companies to build boards that go into this chassis. So as we've built it initially, it's a 40 gig board because we've taken the wedge platform and plugged it in. But as we go to build 100 gig or 200 gig or 400 gig, you should be able to just plug these cards in. And the same thing with different chipsets. If you wanted to build it with different chipsets, you can actually start building boards that are different chipsets onto the platform itself. Okay? So as I said, we'll talk in great detail about the design and what it looks like. But this box is now running in a few places in our production. So we call it our production testing model. A lot of people ask, where do you test? We test in production every time. It's kind of an interesting concept. What's next? So from a next perspective, as we start building a lot more boxes, obviously the interface, our interface becomes the chipsets that are, or the silicon that is running in it. And what feature functionality do we need on it? What capabilities do we need on it? So there's a lot of interaction that we have ongoing with a lot of the chip vendors. So heavily engagement there. The harder problem in the data center space is going to 100 gigs. 100 gigs at an interconnect level inside the data center where we need thousands of interconnects. It's not economically feasible to actually deploy 100 gigs. So working with the industry to come up with the optics solution that makes sense for a data center environment that we can deploy large-scale 100 gigs is one of the things that we're working on. The transition from 100 to 200 to 400, that's actually really interesting, where if you look at this topology where we've actually taken and blown up the CSWs into smaller boxes, we use a lot of interconnects. So the fiber cost inside a data center become actually really interesting. They become quite meaningful numbers in terms of how much money we're spending just on fiber plants. So if we had to go from 40 gigs to 100 gigs and replace all fiber, that would be cost prohibitive. So what we really want is the fiber plant inside the data center to be actually amortized over the life of the data center. That also gives us a upgradability path where if you're going from a 40 gig to 100 gig and you can just essentially pull out the line card and put a new one in and use the same fiber, you can get done much quicker. Replacing fiber on the data center floors takes a lot more time and effort. Right? Time is money, because if you have a data center floor sitting there not being used, you're burning a lot of money because you're essentially wasting power. So time is really important in that sense as well. So one of the things that we want to do is come up with optical standards that provide interconnects that will scale from today's 40 gigs to 100 gigs to 200 and 400 using the same fiber footprint. And that becomes a really meaningful problem for us to solve. So that's sort of where we're headed. Excuse me. Operational complexity is one of the key things that we worry about. When we started actually thinking about this 2 years ago, at that time we decided that we didn't want to do it just yet. And the primary reason was we didn't think we could manage it, because it was too many ports, too many links, too many manual configurations, too many things to troubleshoot. If something is not working, there are just entirely too many devices in this architecture to be able to do it manually. So the focus primarily became how do we build a structure that actually we can manage this environment. So for example, in a monitoring environment, if you look at any network operations organization, what they end up doing is log into a bunch of devices and run a bunch of commands and try to figure out where things are going. Who here has not done that? That's, if you've done any sort of troubleshooting, that's how troubleshooting happens. What we're shifting to in this model is that we have a heat map that's the entire data center floor that shows you what is the fabric doing at this stage. And then you can have hotspots, and then you can drill down and figure out what is going on in any specific box. So instead of going bottoms up and logging into devices, you're coming top down from a monitoring point of view. This is also very similar to SDN concepts, right? So you're looking and top down. That's the kind of monitoring capability we want to build. Same thing with configuration management. It's all built at the topology level, and then configurations pushed down to individual devices. Engineers don't go and log into an individual device to configure anything by hand. So configuration and monitoring is what's really important. The way we sort of thought about measuring how well we're doing was actually an interesting goal that we took on. One of the things that every network has to do is worry about alerts and alarms, and when things fail, what do we do? And somebody there to watch it. Every network has a NOC. We don't. One of the goals we took on was, can we get to a point where only a single network engineer is watching the network at any given time? And now that's at our size and scale. So that's one of the goals that I'm really, really proud that we can hit. We're hitting that. Only one individual actually watches the alerts and alarms. What happens to the rest? It's all automated. The whole idea is that we build enough software interfaces on top that detection of failures is by software, mitigation is by software. And human beings get involved when software can't do it. If you reduce the number of things that human beings have to do, then you don't need as many people worrying about actually just sitting there watching consoles. What that does also do, is where it frees up network engineers to actually go write more code to actually automate more. So it's actually a very self-feeding mechanism. So our intent is to get to a point where human beings don't actually have to sit and watch alerts and alarms and react to them. It also forces us to build a design that is actually very redundant in a lot of ways, where if a device fails and we have to drop everything and fix it, that's a bad design. We should be able to take it offline and fix it next Tuesday when we have time. And that's one of the design principles we use. So you'll see that throughout the design that we're going to present in a little bit. I'm going to close on this last thing. One of the reasons why we're doing even this event, networking at scale, is to start building a community ecosystem where network operators or whoever wants to is developing technology and contributing and sharing, and we build an ecosystem where we leverage each other's work, which, as you heard in the morning, would actually help some startups get better as well. So that's sort of my last pitch, that we're really looking to build an ecosystem of people who are interested in developing technology.